In this video, we're going to take a look at what's called the dot product of two vectors. So we previously looked at how to add vectors, how to subtract, and how to multiply by a scalar, but we have yet to really talk about how to multiply two vectors together, and it turns out it's a little bit more complicated. So the first thing we're going to take a look at is called the dot product. There's another operation that we're going to look at in the near future. So in this lesson, we want to be able to use properties of the dot product, find the angle between two vectors using the dot product, find direction cosines, and find the projection of a vector onto another vector. All right, so let's go ahead and define the dot product. Now, this is more the mathematical definition. In physics, you might use a slightly different definition. They amount to the same thing, though. So the dot product is also called the scalar product or inner product. I typically will refer to it as the dot product. So let's say you have two vectors in the plane in component form u1, u2, v1, v2. The vector u dot vector v, you multiply their first components and then multiply the product of their second component. So you would take u1 times v1, u2 times v2, and add those products together. And then in space, or 3 dimensions, you just extend that to include the third component. So it'd be u1 times v1, u2 times v2, u3 times v3, and then add up those products. But what's really important here is notice that when you do that, when you multiply and add, you're going to end up with a scalar. So the result of the dot product is a scalar, a constant. It's not a vector. So the dot product of two vectors is a scalar, not a vector. So, some properties, which I'll give without proof, but might discuss the proof a little later. Let's say you have three vectors, u, v, and w, and let's c be a scalar. It turns out the dot product is commutative, so u dot v is the same thing as v dot u. If you do a vector dot the sum of two other vectors, it'd be the same thing if you just did u dot the first one plus u dot the second one. So kind of like a distributive property. Let's say you do a scalar times the dot product of two vectors. It'd be the same thing if you just did the scalar times the first vector and then did the dot product with that and the second vector. Or you could do the scalar times the second vector and then do u dot the result of that scalar times that vector. If you do the 0 vector dot any other vector, the result's just going to be 0, not the vector, the scalar, 0. And if you take a vector dot itself, you just get the square of its magnitude. All right, so let's just practice with a few of these properties here. So let's say we have u in component form is 2, negative 2, and v is 5, 8, and we have another vector w, which is negative 4, 3. And let's say we want u dot v. So using the definition, that's going to equal 2 times 5, multiply their first components, then negative 2 times 8, and add those together, and get negative 6. So if we do the dot product of u and v, we get negative 6 in this case. So again, it's a scalar. In B, we want to take that dot product and multiply it by another vector. Multiply by another vector. Well, we know what u dot v is. We just did it. So it's negative 6. And then we want to multiply that by vector w. So we would get 24, comma, negative 18. So the result there is a vector because we're taking the dot product, which is a scalar, times another vector. So we get a vector as a result there. For C, we want to do vector u dot 2 times vector v. Well, one of our properties said that it'd be the same thing if we just did the scalar times the dot product of u and v, which we already know is negative 6, so that'd be negative 12. So since we already knew what u dot v was, made that pretty simple. And the magnitude squared is the same thing as the vector times itself, dot itself, I guess would be a better way to say that. So vector W dot vector W. So let's see, that'd be negative 4 times negative 4 plus 3 times 3. So it'd be 16 and 9, that'd be 25. So the square of the magnitude of vector W is 25. Okay, so we've got our dot product, we got some properties. It turns out we can use that to find the angle between two vectors in the plane, or in a plane. Alright, so if you want the angle between two vectors in a plane, well, let's have theta be that angle. So we'll have theta as the angle between two non-zero vectors, vector u and vector v. Well, cosine of this angle will equal the dot product divided by the product of their magnitudes. So we do the dot product of the two vectors and then divide by the length of vector u times the length of vector v. And that angle will be between 0 and pi, or equal to 0 and pi. Well, if we multiply both sides by the product of those magnitudes, we get that the dot product equals the product of their lengths, or magnitudes, times cosine theta. So that's another way to think of the dot product, is as the product of their magnitudes times cosine of the angle between them. So it's my understanding that's more the definition that is used in physics. I'm not a physicist, but that's my understanding, that this way of thinking of the dot product is more their definition. Well, let's take a closer look at that. We know that this magnitude would be positive, this would be positive. So if we multiply them together, that quantity is positive. So if that's held positive, then the dot product and cosine of the angle are always going to be the same sign. So if cosine's negative, that's going to force the dot product negative. If the dot product is positive, that means cosine theta is positive. So they're either both positive or both negative. So with that in mind, let's think about what happens to these as the angle goes from 0 to pi. Well, if the angle is pi, so let's say the angle between two vectors is pi. Alright, well, that'd be kind of like a straight line. So here's vector u, vector v. The angle between them is pi. And cosine of pi is negative 1. So if this is negative, then the dot product would be negative. So in this case, the dot product is negative when the angle between them is pi. If the angle is bigger than pi over 2, but not quite pi, so you have some sort of, obtuse angle here, cosine would be negative. So cosine for those angles is negative, making the dot product negative. So in those two cases, the dot product would be negative. Now, if the angle between u and v is pi over 2, cosine of pi over 2 is 0. So if this is 0 times this would be 0, then the dot product is 0. So that's going to be an important implication here soon, that if the dot product is 0, we're now going to have two vectors that meet at a right angle. So in other words, the angle between them is pi over 2 or 90 degrees. Well, if the angle between them is between 0 and pi over 2, then cosine would be positive in that case, making the dot product positive. So if the angle between them is acute, then the dot product would be positive. Now what if the angle is 0? If the angle is 0, then cosine of 0 is 1, and our dot product would be positive. And basically that would just mean that the vectors lie in standard position, would lie on top of each other. So they're parallel. Okay, so where did this formula come from? So how do we know that that's actually the formula for the angle between two vectors? So it turns out it's fairly straightforward if we remember our trigonometry. So let's say in the plane you draw vectors u and v in standard position. The angle between them would be theta. And if you form a triangle, then the other side would be vector v minus vector u. So we'd have this triangle with this angle being theta. Well, in trigonometry we learned that that angle and the three sides are related via the law of cosines. So specifically, if we do cosine of theta, we multiply that by double the lengths of the sides here with vector u and vector v. So it kind of depends on how you were taught or thought of the law of cosine. So basically, the side that's represented by vector v minus vector u, that's opposite the angle theta. So that side, the length of that side squared, should equal the sum of the squares of the lengths of the other two sides minus double the product of the lengths of the other two sides and cosine of theta. So the length of this side squared should equal the length of this side squared plus the length of this side squared minus 2 times this length times cosine of that angle. Well, let's actually find those lengths. So this length here, squared, we go ahead and actually find their lengths, their magnitudes. We end up with v1 squared minus 2v1u1 plus u1 squared plus v2 squared minus 2v2u2 plus u2 squared. And the length of u squared would be u1 squared plus u2 squared. There's no radical because everything's being squared. And the length of v squared is v1 squared plus v2 squared. So now if we plug all that in up here, we end up with, I could probably create a little bit more room here. So if we plug that in, so it's going to plug this expression in right here. So we'd have v1 squared minus 2v1u1 plus u1 squared plus v2 squared minus 2v2u2 plus u2 squared. And that'll equal this length squared plus that length squared. Let's see, minus 2 times that length times cosine theta. Alright, so a little bit of algebra. If we subtract v1 squared from both sides, those will go away. If we subtract u2 squared from both sides, u1 squared from both sides, v2 squared from both sides, and then we divide everything by negative 2, so divide everything by negative 2, then we are left with v1 u1 minus v2 u2, I lied, plus, because we divide everything by negative 2, equals those two magnitudes being multiplied together times cosine theta. And v1 u1 plus v2 u2 is the dot product. So that's u dot v. And there's where we get, of course we divide both sides by the magnitude of u times the magnitude of v, but there's where we get this equation here, this relationship here. So with a little bit of trig, it's easy to see where that comes from. Alright, so earlier we talked about how if the angle between them is pi over 2, then cosine would be 0 and the dot product would be 0. So here we go. Some vocab. Orthogonal vectors. So orthogonal vectors. When we say two vectors are orthogonal, what we mean is their dot product is 0 and that they meet at a right angle. Meet, I don't know where my T went, it's meet at a right angle. So orthogonal vectors are two vectors where their dot product is 0 and they meet at a right angle. So we're starting to get a lot of words that mean something similar. So just kind of help you out with the difference between orthogonal, perpendicular, and then something we're going to call a normal. You may have discussed normals in calculus earlier, but if not, we'll talk about it in this course. So if you have two vectors that meet at a right angle, we call those vectors orthogonal vectors. So if two vectors meet at a right angle, they're orthogonal. If two lines or two planes meet at a right angle, we say perpendicular. So two lines or planes meet at a right angle, we say perpendicular. But if it's two vectors, we say orthogonal. If a vector meets a line or a plane at a right angle, we say that vector is normal to those. So a vector is normal to a given line or plane if they meet at a right angle. So we got all these words that kind of mean the same thing. Alright, so let's practice finding the angle between them. Not much to it. Use your calculator a little bit if we need to. So let's say we've got these four vectors, u, v, w, and z, and we want to find the angle between certain ones. Let's say we find the angle between u and v. We can do that. So to find that angle, cosine of that angle we're looking for would be their dot product. So that'd be 3 times negative 4 plus 1 times 0 plus negative 2 times 2 divided by the product of their magnitude. So the magnitude of u would be 9 plus 1 plus 4. So principal square of 14. The magnitude of v would be 16 plus 0 plus 4, that would be 20. So we end up with negative 4 over the square root of 70. So cosine of this angle equals negative 4 over the square root of 70. So we do inverse cosine to get the angle. And in radians, that angle is about 2.069. So notice the dot product was negative, making that angle somewhere between pi over 2 and pi. And 2 radians is exactly that type of angle. So it'd be, on the xy plane, that angle would be in quadrant 2. Well, how about the angle between vector u and w? So cosine of that particular angle, let's do their dot product. So that'd be 3 times 1 plus 1 times negative 1 plus negative 2 times 2. The magnitude of u, we already know, is 14. The magnitude of vector w would be 1 plus 1 plus 5 would be, or plus 4, 2 squared is 4. This would be 6. And that comes out to be 0. So cosine equals 0 at pi over 2. Remember, our angles are only 0 to pi. So we would say vector u and vector w are orthogonal, because the angle between them is pi over 2. How about v, the angle between vector v and vector z? So cosine of that particular angle, let's see, we're doing v and z, so we need their dot products. And the magnitude of v is principal square root of 20. Magnitude of z, that'd be 4 plus 0 plus 1 would be 5. So that comes out to be negative 1, making the angle between them pi. Alright, so just a little bit of practice finding the angle between two vectors. Not too bad. Okay, so now, keeping with this whole idea of angle, we're going to move on and discuss how you can describe the direction of a vector using angles. So if you want to describe to someone that, vector v is pointed this way or in this direction, you can do that with an angle. So if you're in 2 dimensions in a plane, then basically the idea is you use the angle that's in standard position that we discussed in trigonometry. So say you have an angle v, not an angle, sorry, let's try that again, vector v. You just you find the angle in standard position, meaning its initial side is the positive x-axis and its terminal side is the vector. And using that angle, you can use that angle to articulate which way v is pointed, or the direction of v in standard position. So if vector v is in the direction of 30 degrees, you draw a 30-degree angle, start at the origin, and it's headed towards as you know, the direction is along the terminal side of a 30-degree angle in standard position. But it gets more complicated in 3 dimensions, in space. So in 3 dimensions, we're going to bring out our unit vectors here, unit vector I, j, and k. So I runs along the x-axis, k runs along the z-axis, and j runs along the y-axis, and they're all 1 unit in length. So we're going to use those. And the way we describe the direction of a vector in 3 dimensions is we use the angles between these standard unit vectors and the vector we are interested in describing its direction. So they just call v in this picture. So our textbook calls the angle between vector k and any other vector v, the angle between them calls them gamma. And then the angle between vector I and vector v they call alpha. And then the angle between j and v they call beta. So we call those the direction angles. So if I gave somebody those 3 angles, they should be able to visualize which direction a vector is pointed, whose initial point is the origin. What we call cosine of those angles, the direction cosines. Call them the direction cosines. Okay. So, how do we find those 3 angles? So we need to turn our attention to how do you find alpha, beta, and gamma. Alright, so here we go. So let's focus on alpha. So let's say we wanted angle alpha. Well, that is the angle between vectors I and v. That's the angle between I and v. We know how to find the angle between 2 vectors in a plane, so let's do it. So to find the angle between vector I and v in the plane, it would be the dot product equals the product of their magnitudes times cosine of that angle, which we were calling alpha. So that's the formula we just got done discussing. Well, let's do the dot product of v and I. So it'd be v1 times 1 plus v2 times 0 plus v3 times 0. Because remember, I in component form is 1, 0, 0. And the length or magnitude of I is 1. So we just end up with the length of v times cosine alpha. So we clean that up. We get v1 equals the magnitude of v times cosine alpha. We divide. It turns out cosine of the angle between I and v is just v1 divided by its magnitude. So in other words, if you want this angle alpha for a given vector in standard position, you just simply make a ratio of its first component divided by its length. And then you do inverse cosine to get the angle. So we could just do a similar calculation and see that cosine of beta, which is the angle between vector v and j, the standard unit vector j, would just be the second component divided by the magnitude of v, and then do inverse cosine to get the angle beta, and then cosine of gamma would be v3 divided by the magnitude. So it turns out with a calculator, this is pretty quick to come up with. So let's find the direction angles for this vector, 2i, 3j, 4k. Well, we need its length, so let's get the magnitude or length of that vector. So you'd have 2 squared plus 3 squared plus 4 squared. And its length is principal square 29. So cosine of angle alpha is the first component of vector v divided by its length. Inverse cosine tells us that this angle is about 68.2 degrees. Well, cosine of beta, we take the second component and divide by its magnitude of v. Inverse cosine tells us that beta is about 56.1 degrees. And then gamma, we take the third component, divide by the magnitude, inverse cosine, and we get about 42, a little bit of rounding going on here. So those are the direction angles. So with those 3 angles, you could articulate those to someone, and they should be able to visualize where vector v is pointed. So just to see this in 3 dimensions, let's go ahead and take a look at some software here. So we can actually see these direction cosines, these direction angles in action here. So I've got our vector v graphed right here. So it terminates at 2, 3, 4. Terminates at 2, 3, 4. So it terminates at 2, 3, 4. We're in standard position. And we've got our three angles. And let's see if they check out on the software here. So if you zoom in, you can see I've got the standard unit vectors graphed here. They're hard to see, but they're there. There's a little arrow. There's a little arrow. There's a little arrow. And then I've got the direction angles graphed. So there's this angle right here, that pink one, the green one, and the grayish, blackish angle. So there they are. 56.1, 68.2, and 42.03. So that's right on what we calculated. So if you get rid of the axes, it might be a little easier to see. So there's our three standard unit vectors, and then our vector v, and the direction angles that we calculated: 68.2, 42.03, 56.15. All right. So with the idea of the dot product and angle between vectors, we can now discuss something called projection. So earlier we talked about how if you add two vectors together, you get what's called a resultant vector. And we did some practice with that. Well, what if we knew the sum, we knew the resultant vector, and we wanted to, decompose it into the two vectors that added together to get you that resultant vector? So an example of such a situation would be, let's say you had a boat that's being that's sitting on a ramp, getting ready to be released into the water here. So this boat on this ramp, there's a force that wants to pull it down the ramp. There's a force pulling it against the ramp. So let's call W1. Let's call W1 the force that would be needed to keep the boat from rolling down the ramp. So there's a force in this direction that's trying to have it go down the ramp. So there'd be a force that we would need to work against it to keep it from rolling down. Well, W2 is the force, would represent the force that the tires need to withstand. And then if you add those together, you get vector F here, which would be the force due to gravity that's pulling the boat down and against the ramp both at the same time. So W1 plus W2 would be F, and F is basically representative of gravity pulling on this boat. So W1 plus W2 would equal this gravity force. Well, that's the force that we would know easily in this situation. So we can figure out vector F pretty easily. It'd be a little bit more work to figure out what W1 and W2 are. So we would know the resultant vector and we might want to know the two vectors that summed to that resultant vector. So with that in mind, let's discuss what a projection is. All right. So we're going to let vector u and vector v be non-zero vectors. So they're not the zero vector. They actually have a magnitude. We're going to have u be the sum of two other vectors. So it's kind of like the resultant vector. So we got W1 plus W2 is going to equal u. So in my first picture, here's W1, here's W2. You add them together, you get u. Well, we're going to have W1 be parallel to another vector we're going to call v, and W2 be orthogonal to this other vector we're calling v. So u and v are actually the important vectors here. W1 and W2 are the two vectors that add up to vector u. So theta is going to be the angle between vector v and vector u. And if that angle is obtuse, or more than 90 but not quite 180, then the change is that W1 and v would be headed in opposite directions, because we need w1 and w2 to add up to u, but orthogonal to v. Alright, now w1 we're going to call the projection of vector u onto vector v. And we denote it this way, proj, subscript, vector v, and then argument vector u. So what is that? Well, you can kind of think of it as the shadow of vector u onto vector v. So like we've got this right triangle here, and then u, its shadow would be right here. So this is what we're calling the projection of u onto v. In this picture, with an angle more than 90, u, its shadow would be down here. So we got this right triangle, so this one's shadow would be right here. So this is the one we're calling the projection. So we're projecting vector u onto v, but in this case, v and the projection are headed in opposite ways. Well, w2, what we're calling w2, the one that's orthogonal to v, we're going to call that the vector component of u that's orthogonal to v. And the way you would find it is you would just take vector u and subtract the projection, because w1 plus w2 equals vector u. So if we want w2, we just take vector u and subtract the projection. Okay, so how do we come up with this projection? Well, we're going to start with some trig. Everybody's favorite, right? So notice in both pictures we have a right triangle. So I'm going to steal this one right here. This one right here. So we have a right triangle. And then if we do this angle theta, then cosine of that angle theta would be the adjacent side, which we're calling the projection, divided by the hypotenuse, which is represented by vector u. So using our right triangle trig, cosine of theta would be the length of the projection divided by the length of vector u, the hypotenuse. But in the case where the angle is bigger than pi over 2 but less than pi, so that would be this case right here, in that case, cosine would be negative, because cosine of an angle bigger than pi over 2 but less than pi is negative. So if cosine's negative, and we know this is positive because it's magnitude, then this would have to be the negative part. But length can't really be negative. That kind of doesn't make sense. So instead of thinking of that as the length of the projection, since it could be negative in this case, we have a different name for it. We actually call it the component of vector u in the direction of vector v, or the notation for that would be COMP subscript v argument u, and that'll be a constant because it is a length. Could be positive or negative, but still it's a constant. So we're going to call that constant k. So k is a scalar. So instead of thinking this is the length of the projection, we're going to think of it as the component of u in the direction of v, and it's a constant. Could be positive, could be negative. We're going to call it k. So we're going to call that k. So cosine of the angle between u and v would be k divided by the length of u, just using right triangle trig. So multiply both sides by the magnitude of u, then k is the magnitude of vector u times cosine of theta. Theta is the angle between u and v. So k could be positive or negative, because cosine could be positive or negative. So basically just think of k as the signed, which just means positive or negative, magnitude of the projection. Okay. Well, theta is the angle between u and v. And we have a formula for that. So the dot product equals the magnitude of v times the magnitude of u times cosine of this angle between u and v. But cosine of theta times the magnitude of u, we were calling that k. So back up here, k, using our right triangle trig, k is actually the magnitude of u times cosine theta. So if we make that substitution, we have the dot product equals the magnitude of v times k. And remember, k is the length, positive or negative, of the projection. So if you divide by the magnitude of v, you get k to be the dot product of u and v divided by the magnitude of v. In other words, k can be written without the angle. So we know how to find k with the angle, but we now have a way to write k without the angle. It's the dot product divided by the magnitude of v. So going back to our picture, we want the projection to be parallel to v. The projection should be parallel to v. So to make that happen, we want the projection to be parallel to v. So two vectors are parallel if one is a scalar multiple of the other. So our projection, this is a scalar, k is a scalar. It's a dot product divided by a magnitude. That's a scalar. So we want our projection to be a scalar multiple of v. So to make that happen, we're just going to take k, which is the magnitude of the projection, positive or negative, and we're going to multiply it by a unit vector in the direction of v. So rather than v of any magnitude or length, we're just going to go ahead and have it be length 1. So our projection is going to be this scalar times the unit vector in the direction of v. So when you multiply those together, you're going to get a vector, and they'll be parallel. So if we make a substitution for k, we get that the projection of vector u onto v is just k, which is the dot product of u and v divided by the magnitude of v, times a unit vector in the direction of v, which is vector v divided by its length. Multiply those together, you get the dot product divided by the square of the magnitude of vector v times vector v. So that will give you a vector. So the projection is a vector, and this is a way to find it. It's a formula for it. So here we go. So the vector projection of u onto v, we have a formula for it. So the projection of u onto v is the dot product divided by the square of the magnitude of v, this one, times vector v, where k was that dot product divided by the magnitude of v. We were calling that, this is from earlier, we were calling that the component of vector u that's in the direction of vector v. A lot of vocab here. A lot of vocab. Okay, so basically, we now have a way knowing u and v to come up with this W1 right here, this projection. And if we know u, v, and this W1, we then can get this W2. So tying this all together, u is the sum of W1 and W2. So if I have u, which is the sum of W1 and W2, and I want to decompose it into W1 and W2, I now can find the projection, and with u and the projection, I can find W2. Alright, so let's practice with this. So let's say we want the vector component of u, which is 5, 10, that's orthogonal to v, which is 4, 3, and we know the projection is 8, 6. So again, what we're going to do here is we're just going to, without any story attached to it, we're just going to quickly show how if you have u and the projection, you can now figure out which two vectors added up to u. That's kind of the idea here. So we know that W1 plus W2 is u. So W2, the one we don't know, that we're calling the vector component of u, would just be vector u minus vector W1, or the projection. So that's going to be 5, 10 minus the projection, which is going to be negative 3, 4. So this just quickly shows that we now can take a vector u and decompose it into the vectors that added up to it. So if we think this could end up being a resultant force, and we can figure out which two forces are added together to give you that resultant force. but it requires that we do know the projection. All right, so what if you needed to find the projection? So let's say you've got a vector u and a vector v in standard position, and you want to find the projection of u onto v. So now we actually want to come up with the projection. Well, that's what we have our formula for. So w1, which we were calling the projection, is the dot product of u and v divided by the square of the magnitude of v. So that's 49 plus 1 is 50, plus 40 54. But we square that. So we take that times vector v. So times 7. So this is a scalar. We multiply through our vector, and we get 14/9 vector I plus 2/9 vector j minus 4/9 vector k. So now we know the projection. So if I want W2, so in other words, here's the projection, which we were calling W1. So this plus some other vector should add up to u. And what if we want that other vector, which we were calling W2 in our picture? That's going to be u minus the projection. So that's going to be 3i minus 5j plus 2k minus 14/9 I plus 2/9 j minus 4/9 k. If we do that subtraction, we get 13/9 I minus 47/9 j plus 22/9 k. So basically this one plus this one should equal u. So it's kind of like taking a vector and decomposing it into which vectors added up to it. All right, now let's actually put this to some real-world use here. So let's go back to our boat. So we've got a boat that's sitting on a ramp that's inclined 30 degrees. So we've got some water, got a ramp. The ramp is inclined at 30 degrees. So here's the tire, here's my boat. It's a good boat. Now that boat weighs 600 pounds. And it says, what force is required to keep the boat from rolling down the ramp? Well, if all we know is the weight and the incline of the ramp, which are both easily measured, relatively speaking, we can figure out what force is required to keep it from rolling down the ramp. So gravity is acting in this direction, which would be straight down, so on the xy plane. On the xy plane, that would be negative 600j. So it's a 600-pound boat, so its magnitude should be 600, but it's in the negative direction because we're headed downward. And then j is the unit vector along the y-axis. So that's gravity. So the idea is that that vector is the resultant vector of, say, this one and this one. So that'd be 90 degrees. So if we add those two vectors together, we get vector f. And that's what we ultimately want to know. The reason we want to know that is, if we know the force by which is going in this direction, then we would just want to keep it from rolling down the ramp. We just need to know how to balance it out with a force going in the opposite direction. So I just need to know this magnitude, and then I'll know exactly how much to force in the opposite direction to keep it from rolling down. All right, so let's say that vector is the one that's acting in the opposite direction. Let's call that V. This will be our projection, so we'll call this one W1 and this one W2. So our projection, remember, is the shadow of this one right here, what we were calling U in our generic picture, but as we're calling F here. So W1 is the projection. Alright, so what about this vector V? Well, V, let's just go ahead and have it be a unit vector for now. So V, let's see, that would be cosine 30 degrees I plus sine 30 degrees J. So here's V, and then on its own little plane, that'd be 30 degrees. So it'd be 30-degree angle in standard position. So it'd be cosine 30 degrees I plus sine 30 degrees J. It's a unit vector, so its magnitude is 1. So V would be root 3 over 2I plus 1/2 J. But we want V and W1 to be parallel. So we want V and W1 to be parallel. So with that in mind, W1, because I want it to be parallel to V, which we were calling the projection, that was what we were calling the projection of, let's see, we're projecting F onto V. Use our formula for the projection. So we're going to do the dot product of F and V. So the dot product of F and V would be 0 times root 3 over 2 plus 1/2 negative 600 divided by the square of V's magnitude, which is 1. And we multiply that times V. So W1, which is the projection, is going to be negative 300 which is really the only part that we want, because the magnitude of that is 300. So what that's telling me is, if there's 300 pounds of force acting in this direction, then I need 300 pounds of force in the other direction to keep it from rolling down the ramp. So we need 300 pounds, because 600 was in pounds, of force.